Introduction. What do you notice about the traffic at the busy junction? The numbers of vehicles entering and leaving the junction are equal. When current flows in a circuit, the rate of electrons flowing into and out of a junction are the same. The simple idea is summarized by Kirchhoff's laws. In this lesson, you will learn and use Kirchhoff's first law. Learn and use Kirchhoff's second law. Use Kirchhoff's laws to solve problems. Click the switch button. Then click the junction button in the circuit to have a zoom view of the flow of electrons. What can you infer about the rate of flow of charge into and out of the junction? Click the conclusion button. Kirchhoff's first law is based on the principle of conservation of charge. Whatever charge that goes into a junction must emerge from it. Click the first law button for the full statement of Kirchhoff's first law. Click the switch button and observe the readings of the milliammeters. Test. Key in your answers for the current I1, I2, I3 and I4 in the above circuit. Summary. Kirchhoff's first law states that at a junction, sum of currents entering equals sum of currents leaving. Kirchhoff's first law is based on the principle of conservation of charge. The carriage of the roller coaster gains potential energy when it is being pulled up to the top of the track. As the carriage moves down, its potential energy is converted into kinetic energy. Similarly, in an electric circuit, the source of EMF such as battery raises the electric potential energy of the charges. As the electric charges flow in the circuit, the electric potential energy is converted into other forms of energy. Energy is conserved. Kirchhoff's second law is based on the principle of conservation of energy. Kirchhoff's second law states that for a closed loop, algebraic sum of the EMFs equals algebraic sum of the products of the current and the resistance. Sigma E equals sigma IR. When applying Kirchhoff's second law, the direction of the loop is arbitrary. The signs for the currents and those for the EMFs, whether positive or negative, are determined by the direction of the closed loop. The current or EMF is considered positive if it is in the direction of the loop and negative if in the opposite direction. Click the closed loop ABCDA button to observe the direction of the closed loop ABCDA. In the circuit, is I, E1, E2 positive or negative? Click on each of the possible loops in the circuit. For each loop, state the sign positive or negative for each of the EMFs and currents. Two cells, each of EMF E1 and E2, and internal resistance R1 and R2 respectively are connected to two resistors R1 and R2 as shown. The current in the circuit is I. In the closed loop ABCDA, what is sigma E, the algebraic sum of the EMFs? Click sigma E equal button. What is sigma IR, the algebraic sum of IR? Click sigma IR equal button. Then click sigma E equals sigma IR button. Summary. Kirchhoff's second law states that for a closed loop, algebraic sum of the EMFs equals algebraic sum of the products of the current and resistance. Sigma E equals sigma IR. Kirchhoff's second law is based on the principle of the conservation of energy. The current or EMF is considered positive if it is in the direction of the loop and negative if in the opposite direction. In the circuit shown, use Kirchhoff's laws to find the values of the current I1, I2, and I. Click Use the first law for the point C button. Click the Use the first law for the point C button. Summary. To apply Kirchhoff's laws, use the first law for each junction. Use the number of independent equations should be the same as the number of unknowns. The same milliammeter of full-scale deflection 1 milliampere and resistance 170 ohm may be converted into a voltmeter. Click on the milliammeter to pass a current of 1 milliampere or 0.001 ampere through the milliammeter. Click on the Potential Difference Across Meter V1 button. To change the milliammeter of full-scale deflection 1 mA to a voltmeter, a resistor is connected in series with the meter. Click the voltmeter button. A teacher has converted a 10 mA milliammeter with internal resistance 20 ohm to a voltmeter with full-scale deflection of 20.0 volt. Click on the meter to view how the teacher connects the multiplier of resistance R inside the meter. Try to calculate the resistance of the multiplier, then check your answer. When a student uses the voltmeter, which had been converted from the milliammeter by the teacher, what is the voltage being measured when the pointer is at the scale marked 2, 4, 6, 8, and 10? Click on the meter to see the scale of the meter after it has been converted to a voltmeter. Summary: to convert a milliammeter to a voltmeter, a high resistance resistor, known as a multiplier, is connected in series with the meter.